Yeah, so we're going to finish up the immunology lectures. Today we're going to talk about phylogenetics. And so I'm going to share my screen with you. And as soon as I can find where it is among all this stuff. Okay. All right, so we're going to talk about phylogenetics today. Turn this guy off back here. Just making things bright. So phylogenetics, yeah. So pathogens, like humans and everyone else, we're all living things, and so we've descended through a lineage of a lot of other living things. And so, where are we? What can we do with phylogenetics is the big question. So we can deduce relationships among species or genes. So basically find out if pathogen A is related to pathogen B, or if there are distinct strains or genetic profiles of different pathogens within the same species. Make inferences about the origin of pathogens. If we know where they are and how they're related to other things, we can get an idea of how they might have descended and arose. This is particularly important when we're talking about emerging infectious diseases and zoonotic pathogens, is learning where they came from, because this helps inform how we deal with them, how we treat them, how we create medicines or vaccines. Identify biological processes that affect how your sequence is involved. Identify genes and residues undergoing positive selection. So what traits of this particular pathogen are being selected for right now? Is it becoming more virulent, less virulent, more transmissible, less transmissible? Is there no change? These are things we can do with phylogenetics. Explore evolution, estimate the timing of major historical events, estimate the impact of geography on species. Is there, like with HIV, this was a question, were there sort of different regional variants of HIV? Yeah, so what is a phylogenetic tree? A phylogenetic tree is an explanation of how sequences evolved, how their genealogical relationships, and thus how they came to be the way they are today, or at the time of sampling. So you think about this, here's a picture that Darwin drew in 1837, illustrating how different species branched off from other species to become what they are today. We think of this as a tree, or clade in biological terms. And the topology of the tree itself describes the branching structure of the tree, which indicates patterns of relatedness. So there's a common ancestor here between A, B, and C. A and B have a common ancestor here. C is only related to A and B through this common ancestor back here. Yeah, so all these are the same. And these trees here display different topologies. So A is related to B through this node, and A and B are only related to C through this node. Branch lengths indicate genetic change. Longer branches indicate greater change. Change is typically represented in the number of substitutions per site, but you should check the legend of any figure that you look at. And I have to say that you don't always see this, for pathogen search, sure, certainly you do, but sometimes you just see trees, because it's often genetic change can be somewhat difficult to get at in some cases. So if you don't see numbers, don't be surprised what I'm saying. A scale bar can represent branch lengths. So here's your scale bar here to tell you different branch lengths instead of the numbers here. Distance and substitution rate are confounded. Branch lengths indicate the genetic change has occurred. We often don't know if long branch lengths reflect a rapid revolutionary rate, an ancient divergent time, or a combination of both. So there's kind of some unknowns here. You can only tell how different the different organisms are. How good is the tree? A tree is a collection of hypotheses. So we assess our confidence in each of its parts or branches independently. There are three main approaches: doing bootstrap, Bayesian methods, approximate likelihood ratio test methods. These are very specialized analyses, both as an art and a science. So obviously, it's, you know, like all statistical questions, it's important to consult an expert. Genetic data is extremely big. So sort of traditional methods of assessing relationships can be challenging because basically you've got so much data that everything can be significant. There's different ways of getting around it that you know, they might not teach you in standard intro biostat courses. So, you know, definitely consult an expert there. But the point is, for this slide, is that genetic data is huge. In reality, of course, there's only one true tree. The true tree refers to what actually happened in the evolutionary past. Obviously, we can't know everything. We can only infer what has happened by what we see today, what evidence we're given today. All methods attempt to reconstruct the true phylogeny, which, you know, of course, becomes very challenging. Even the best method may not give you the true tree, so you always have to have a dose of healthy skepticism. You know, in biology, in cladistics, there's this, you know, large debate on, you know, what makes a divergence. Are divergence always complete? Are they a final step? You know, and then, or divergence, does it come back sometimes? I mean, there's all sorts of open questions here. But the point is the true tree. There is a true tree out there. We just can't necessarily know it with the data we have.